Hi, welcome to the Signal Path. In this episode, we're going to take a look at this BK Precision 9185 DC power supply that doesn't work. This is a 400 volt half an amp or 600 volt 350 milliamp power supply. Now, half an amp doesn't sound like a lot, but of course, half an amp at 400 volts is still 200 watts. So it is a pretty capable power supply. Now, the reason I bought this broken from eBay was because this is actually a linear power supply. It's not a switching power supply. So it's a precision supply all the way up to 400 volts. It should be fairly low noise and low ripple, unlike the switching power supplies which are often found in this range. And I wanted always to have a high voltage power supply that's linear to do some precision experiments at higher voltages. Now I'm in the middle of actually reviewing something, and it's right over there. So I'm doing some experiments and preparing that review, and these reviews typically take a long time. So I thought we'd take a break and take a look and see if we can repair this unit. And I can't actually turn it on right now, and there's a reason for that. Let me show you why. And well, can you see why I can't turn it on? Well, it's missing the power plug, of course. Someone has taken it out, and I can see the earth ground cable sticking out over here. So someone has taken this out and cut the cables or done whatever with it. Maybe because it was completely broken and they just salvaged that part. I hope it's not missing anything else on the inside. I'm not sure. And also we're going to have to take a look and see what's going on in it. And at the back we have the sense ports and a USB control, which is fantastic. It's standard USB. It does have two expansion ports here, which are empty, but I looked it up, and you can put things like RS-232, GPIB, analog control stuff over there. Not really exciting. It really has everything that you would really need, especially because it does have a USB port and a software to control it. So I'm eager to take a look inside, and this is a very long unit, and you can't probably tell from that angle, but of course, because it is a linear one, it's going to have a big transformer in there, and you can see the big heatsink in there. It's going to have lots of transistors on it that is going to be required for regulation. So I'm very eager to take a look at the quality of the construction inside and see why this is missing and see if it's safe to turn on. All right, let's go ahead and remove the cover. I've already taken the screws out and see how it looks like. And there we go, and look at that. Looks very nice, very clean design. I like it. So let's take a look and see if we can identify some of the components. Obviously, as I said several times already, linear power supply, huge transformer turret in there. That's the whole of the turret transformer. I can see it from the side. Lots of these ferrite cores in several different places to just create a little bit more filtering, suppress some of the noise that comes out of this. This is a low noise power supply after all. So the connections from the power supply, from the toroid, go all the way over here. Most likely a bunch of, I can see already one bridge rectifier here, perhaps some more rectification, big capacitors. Some more over here. These are 315 volts, 820 microfarads. So obviously they're going to be in series in some fashion. Nippon Chemicon brand, excellent, good quality components. BK Precision makes good instruments. Yeah, it's just too bad they're not that popular. At least I don't see them very often, although I do have a few of them here in my lab. Here's the where's the input there? This is where the power comes in. Here's our earth ground here in the corner. So I'm just trying to find out where it actually ends up. And it looks like it ends up right over here, right there by the power switch. Right there, so I can see blue and brown written there. So these are colors, of course, for the European Union for indicating blue being neutral and brown being live. That's different from North America, where black is live and white is neutral, or silver is neutral. So don't make that mistake. Black is not ground. That's very different from electronics than it is for power electronics. And that's a big mistake. If you mistake those two, it could be your last one. And so here's the heatsink. Air is flowing through the fins in the middle of the heatsink. Look at all these big transistors. These must be quite high voltage devices in order to be able to provide a 600 volt. Of course, because when you set the output of the power supply to a very low voltage, this is a linear supply, you're going to have a huge voltage across those transistors. So we'll take a look at that. Here's the digital board. I can already see the main processor's numbers have been machined off, so you can't tell what kind of microprocessor it's using. I don't think really that helps that much to prevent people from copying it, but anyway, at least the transistors, I can see the marking on them still. So you know what, it looks very good. It's very clean. I don't see any sign of damage. The transistors all look good, and the other side there is more transistors. I see a little bit of a sign of some flux on that side. I'll show you afterwards, but I don't think that's really a problem. Yeah, so looks good. There's a missing screw there. That's not a good thing. So let's go ahead and maybe, well, I guess I could potentially turn it on, but I am a little bit weary about turning it on, considering that they've taken that cable out. It's surely something must be wrong with it. No one's going to take a cable from something like this if it's working. So let's go ahead and maybe remove this board and see what's underneath it. I can't find any other issues with it. I'm tempted to remove all of these cables and measure the transformer on all of these. Maybe we can do that. But let's go ahead and look and see what's underneath that, where the expansion ports are, and maybe there's a problem over there. And there's a USB connection there that goes underneath. So there is other stuff going on, because obviously this needs to go somewhere. So I'm curious to see that. Looks good so far. Let's take it one step further. Well, check it out. It looks like my intuition about something being wrong with the power supply did pay off. And of course, if you look over here, I don't think this is what this is supposed to look like. Of course, this resistors have been completely destroyed. And if you look very carefully, you can see, let me zoom out over here. I think Pooch is trying to help us here. Yes, Pooch, find the problem. Find the broken components. So if you look over here, there's a big plane over here. This is obviously not plugged in, so don't worry about the cat. And this plane over here is connected to all of these surface mount resistors. And these are all 100 ohm resistors, and there's 3 in parallel, so 33 ohm per transistor there. And they're all sharing this plane over here, and they're all sharing this plane on this side. And it looks maybe the other ones on the other side are joining. So these are, in some of them at least, are in parallel, which makes sense. These are output driving transistors, so they make sense, and they're in parallel and some kind of feedback. And these resistors isolate the transistors from this main plane, which is one of the why this might have actually not had too much damage, because it most likely this transistor is dead and a short of some kind, and that is put a ton of current through these resistors well beyond what they were rated for, and of course totally damaged them and burned them out. So this might have been some level of protection as a result of that. I wonder if they're using this for just low pass filtering or some just isolation protection. I don't have the schematic. We can do reverse engineering on it, but for now it's very obvious what is wrong. A couple of botches around here, some kind of modification. This modification here is also been added, so we have to make sure that we figure out what to do with it. So let me go ahead and order some of these components, come back through the magic of television, and then maybe we'll try and replace these. And before we replace them, we can do some measurements to make sure that's indeed what the problem is. If I remove this, given that it is parallel with everything else, it wouldn't matter. This would still work perfectly fine. So I could remove it and just not put it under complete load and see if the supply turns on and works, or we can just go ahead and replace it if it is indeed dead. So let's do some measurements on it. Okay, let's do some measurements here. So let's start with the one at the bottom here. Let's make a couple of measurements, and then we can do a relative measurement to compare them. So between these two pins, I read 44 ohms, and I'm assuming that I would read exactly the same thing between these two. And there we go. Yep, there you go, about 44 ohms. And let's measure the suspicious one. And what do we read here? We read 0.73 ohms. So yep, that's a short circuit. The other two pins, also a short circuit, and the remaining two pins, and also a short circuit. Yep, this thing is a short all around. If I go to the bottom transistor here, measure that one, yeah, I see charging capacitor. One of the big capacitors is probably charging up. So yeah, so this is definitely dead. And I can go ahead and perform the same measurements on all the other ones and see if I read the same ones. You can see I'm reading the same value on all the other transistors, so they are most likely all fine. And given the fact that only that one shows that sign of damage, it's probably an isolated situation. Yeah. Okay, so that's a good sign. It means that that's dead. We don't have to do some reverse engineering. This is a good first step, and I have to redo this bodge over here to make sure it's exactly like it was before, and then maybe we can turn it on. Now, if you look carefully, Pooch is going to come and he's going to steal a Q-tip. I don't know why he does that, but he always does that. If I leave the Q-tips alone, he's going to eat them. Why do you do that, Pooch? Why? Stop it. Oh God. Alright, and DigiKey has delivered components for us. Here we go. These are surface mount resistors. I bought a whole bunch of them. And what else do we have here? So here's a transistor, and I bought 3 of these. And if you look over here, if this thing would focus, these are 900 volt devices, 15 amps, very high voltage, very good quality components. And I bought 3, $8 each. They're not cheap. So anyway, I bought more than I needed. I'm sure they will become useful in the future. And I bought some more surface mount resistors that were also dead in the process. So now we can go ahead and do some replacement. So the pads cleaned up quite nicely. I was worried that the charred resistors had actually damaged the PCB material, but they haven't. This discoloration that you see here is actually on some of the other pads as well, and I can't really get rid of it. And oh no, maybe I can. I was just cleaning it with acetone and with alcohol. It wasn't coming off, so maybe I'll just put a bit of mechanical force on it and clean it up. But yeah, so it looks good. I'm very happy that the board is not damaged, because if you start burning the board, and then the traces will be bad and the board become resistive. So I'm glad it's not like that, especially because high voltages are present here. You damage the board, you change the dielectric breakdown properties, and then of course everything is down the drain. So since it looks good, we can take it to the next step. Now in order for me to remove the transistor itself, which you can see I've removed the solder, the digital board has to come out. So we can also take the digital board out and take a close look at it. And here's the board, and I'm sorry about the angle. I cannot actually take these cables off. So you can see the main processor, of course, has been machined off. The part number you cannot see, and a few other of the critical components, even these devices, which is very surprising. Some D to A converters, A to D converters there. Everything you can see is up to isolated from the main power supply. So it's really just a digital section. Nothing really unusual about it. There's no point really trying to reverse engineer it, but there's some couple of components here, some common mode inductors and stuff that are not actually populated on this board. Interesting, maybe they use this board for more than one version of this type of power supply. They most likely do, and you can see clean isolation here, completely isolated. So this is the power supply region, this is the digital region, and the processor is going to be on the digital region, of course. So yeah, it makes sense that the connected region to the power supply, where 600 volts and 900 volts or whatever it is going to be present, is going to be separated from the user, especially from the USB port. So it all looks good. Now we can go ahead and remove the suspected transistor and see if there is any actually damage on it. I don't think there is any damage on it. It looks really good. Whatever it is, it has happened internally. So let's take it out. And here it is, an ST microelectronics part. Doesn't look like there is any really visible damage on it. All internally shorted out. So yeah, we can go and replace this guy. And here we are, everything back together. The only component I didn't have was a TVS diode, a transient voltage suppressor diode, which can be thought of as two back-to-back Zener diodes. Now, if you look carefully, I've written here the labels of the transistors, so gate, drain, and source. And this diode over here is between the gate and the source, preventing the gate voltage to have transient effects that can go above a certain voltage. So this is a 22 volt Zener diode. Now, technically, I should put really two of them back to back, but I don't really think in this design the gate voltage would ever spike down well below the source voltage. Anyway, for now, for our purposes, it should be okay. If something goes wrong, we can always change it later. But for the time being, I think this is a good place to start trying to test the power supply. I also made this little guy, which is nothing more than the power cable connected to these two, and I've shrunk them as well as I could. These are really beefy wires, should be able to carry the current without any issues. So let's go and reassemble it, and then we can give it a try and see what happens to it. And here is our finished product. I think everything looks good. Now it's just a matter of testing it and see if it boots up correctly. So I made sure that the power cables is properly connected. Now the fuse that came in this filter, front-end filter here, is actually way too high, so I have to change that. It's 8 amps, and this is a really good fuse holder. It's a dual fuse, so it has a fuse in live and a neutral, and built-in filters, so it's a good one for this power supply. Okay, let's do a power on test here. There we go. That seems promising so far. Checking EEPROM. Wow, that is loud. Okay, so I'm checking for cards. There's obviously nothing in there, so there should be nothing showing up. What are you doing? There it goes, none and none. And there it is, looking good. So this obviously has two ranges. Right now it's set to range low, and the range high will go up to 600 volts, and range low will go to 400 volts. So I should be able to turn the power on. Let's see if something blows up, and oh, that's promising too. So it looks like it reads back the voltage at the output, so it's reading 9.97, and look at how many digits and the current we get. Wow, this is a lot of digits there. So it's interesting to see how accurate this would be. I'd suspect that it probably doesn't have very good calibration if the output is working, but given that it's reading it, I would say it's working. It also has this special type of banana connectors in the front, which are protected so you don't accidentally touch the metal because of the fact that it goes up to 600 volts. So I would say maybe what we should do is connect it to a 7.5 digit meter like the Keithley one that I have, and maybe just run through the calibration cycle and see how well it would behave after the calibration. So let's take a look at a couple of the measurements from this instrument. So I have it connected to my Keithley DMM7510, and as you can see, under 0 volt condition, we're reading basically 0 volts. There's a tiny offset, but it's really nothing. Remember, the scale there is in millivolts. So we come down here, and we can go ahead and enable the 10 volts and see what we read. So here, 10 volts is measuring 9.97, and if I go up there, our 10 volts is reading 9.986, so it's actually really close to what it's supposed to be reading. It's just a tiny bit off. So let's set some other voltages. Let's set the voltage to 100 volts, and here's 100 volts, and that's not bad at all. I mean, we're only off by 10 millivolt there, and in fact the measurement on the instrument also jumps back and forth on this smallest digit there, so it's actually matching what we're measuring. So the question is, do we want to calibrate it such that the measurement reading back is closer to what it's supposed to be? So it wouldn't hurt going through the calibration procedure. Sorry about the camera going back and forth. So I'm just going to keep it over here so we can do a couple of other numbers. So let's do 200 volts. There you go, that's 200, and we're reading on the screen 199.97, and here is 999.98. I mean, it's really good. So let's go 300. That's 300. Again, very good. 400. Also good. 500. And finally 600, which is the highest limit. I think this thing can go a little bit higher than 600. I think 615 might be the maximum, if I'm not wrong. No, it doesn't let me do that. Maybe just for, let's see, 605. Yeah, there you go. You can get 605. Yeah, so it's very accurate. Right now I'm reading 604.93 and it's giving 604.98. So just for the sake of calibration, I think it might be worthwhile trying it out just to see how easy it is to calibrate that. So let me go ahead and set the voltage to something that's a little bit safer. Here's 10 volts there. And if I turn the output off, if I go under menu, there's quite a few settings you can actually set here. Output protection, output settings, program mode, timer function. So it's pretty capable. So the calibration menu is right there. So first thing to do is perhaps reset the instrument. There's IP address, blah, blah, blah. We don't need that. Where is it? There it is, reset. Recall default. Do I want to do that? Yes. So now it's going to get all the default values back, and then we can go through the calibration menu and see how it does the calibration. Now, given that fact that it can only put out half an amp no matter what voltage you set it to, I should be able to just sync the current directly into my DMM and not have to worry about a shunt resistor to measure the voltage across. So that would make the calibration procedure certainly much easier. And 7, calibration. Oh, password. Well, that I don't know. I guess we have to go check to see if it's in the manual. Yep, it is 13579, 13579, and there it is. So we can get current calibration and voltage calibration. We're setting voltage, so let's do a voltage calibration. And it says voltage calibration on channel 1. Yeah, this only has 1 channels anyway. Voltage set 10, and then the reading has to be adjusted. Voltage set 195, and the reading is adjusted. Okay, so what exactly do I do here? There it is. So yes, it is setting 10.387, and I'm reading 10.38. So I guess I'm going to have to adjust that. I'm not sure what that number is. I guess I should read the manual a little bit more carefully. So it turns out I just need to enter the number, so it is pretty easy. So we have 10.380. 10.380, I think that sounds about right. Okay, we go enter. Perfect. Now it's doing 195 volts, so I enter that as well. So 195.25, 195.255. We go enter on that. There you go. Now it goes up a range. So I'm going to go through this and see what happens at the end. And the current calibration process is essentially the same thing. And we're just going to dump some current into the instrument and read it back. So I'm going to go through that also. It's pretty straightforward. And the calibration is done, and the numbers match. It's a little bit better than before. Not that it was very bad before, but it looks good. And I'm reading 101.01, and you can see up there we are reading about the same. So now if I go and set, let's say, to 500 volts, I should get, I'm reading 499.98, and I am basically 499.98, actually reading 0.99 on the instrument. So it looks good. Now the only other thing to check is make sure the current is working, and that will be it. And here's our current measurement, so I have it shunted, so you can see right now the current set is set to 10 milliamp, and we're just under 10 milliamp, and of course up there we read almost exactly the same value, so I'm quite happy with it. We can set it to some higher values. Let's set it to 0.1, 100 milliamp, Here's our 100 milliamp, and it's dead on, exactly as you would expect it to be. And the highest one that I can set right now, I think it's 350 milliamp in this range. So we can set it to 350 milliamp in this range, and we're reading 34998. And on the instrument, we are basically reading the same thing. Now, if I turn the output off and I change the range to low, I can set the current to 0.5 amps, and if I turn it back on, I expect to read, well, just essentially half an amp exactly. And check it out, I would say that's pretty good. So yeah, very happy with this. This is a nice supply, so maybe you can let me know in the comment section some cool experiments that we can do with a high voltage DC power supply of such precision. I have some couple of ideas here and there, but maybe stress testing some components would be interesting. But certainly going all the way up to 600 volts can have some benefits, especially if you can sink 200 watts into something. So let me know what you think in the comment section. As always, again, this is thanks to my Patreon supporters. I bought this broken from eBay, and it's thanks to you guys that I can get these things and fix them. I have a couple of other instruments to repair. I'm going to finish the Roden Shorts review today, hopefully, and post that as well. So I'll see you in the comment section.